All right, let's talk about the strength of conjugate acid base pairs. So remember, if we have a weak acid, it forms its conjugate base, or if we have a base, it forms its conjugate acid. So the Kb, right, the equilibrium constant of a base times its Ka of its conjugate acid should equal Kw, which is our equilibrium constant for the autoionization of water, which is 1 times 10 to the minus 14. So there is an inverse relationship between the Ka of an acid and the Kb of its conjugate base, or the Kb of a base and the Ka of its conjugate acid. So let's look at an example. The other thing that I want to mention, because of this inverse relationship, if we are given the Ka of an acid, we can calculate the Kb of its conjugate base. Or if we're given the Kb of a base, we can calculate the Ka of its conjugate acid using this relationship. So that's what we're doing in this example. We're asked to use the Kb for the nitrite ion to calculate the Ka for its conjugate acid. So we're given the Kb 2.17 times 10 to the minus 11. We can use this relationship here to find Ka. So if we have nitrite ion dissociated in water, its conjugate acid forms, as well as hydroxide ions. There was a delay there. So write that chemical reaction so that you can see that, right? So nitrite ion, its conjugate acid is HNO2. That hydrogen came from water, H2O, so we'll end up with hydroxide ions. And that is what this Kb is based on the amount of those hydroxide ions that we have at equilibrium. So using this relationship here, we can find Ka by just rearranging this equation, right? It's basically Ka times Kb equals Kw. So to solve for Ka, we just divide Kw by Kb. So we do 1 times 10 to the minus 14 over the value for Kb, and we find that Ka is equal to 4.6 times 10 to the minus 4. An important relationship to remember, because in an experiment, you will have to use this relationship to determine either the Kb based on the Ka that's given or vice versa. So what is also true about this inverse relationship, or since there's an inverse relationship, the larger the Ka is of an acid, the smaller the Kb will be for its conjugate base. And the larger Kb is for a base, the smaller the Ka is of its conjugate acid. So it's like we're saying the same thing, but in different ways. We also saw this relationship earlier when we talked about pH and pOH, right? There's this inverse relationship. If we see a low pH, which is due to a strong acid, we will see a higher pOH, right? So we see this inverse relationship between the Ka and Kb, just like we see inverse relationship for pH and pOH. So this is our weak acid. We have a weak acid dissociated in water. right? We're forming hydronium ions and we're also forming the conjugate base of the acid. So the extent to which the acid donates its proton to the water depends on the strength of its conjugate base. And conversely, if we were looking at a weak base, right, the extent to which that weak base accepts a proton from water would depend on the strength of its conjugate acid. So looking at this example here where we're looking at the conjugate base to determine the strength of the acid. So let's say that the conjugate base is a strong base. It's a strong base. What that means is any proton that's donated to water, right, from this weak acid, essentially that interaction won't be strong enough, and instead that proton will be reclaimed by the conjugate base. So essentially, if this conjugate base is a strong base, we'll keep shifting the equilibrium to the left because that free proton or that proton that is coming from the acid being donated to the water, it's basically happier with the base because the base is a strong base. So that would mean, right, if the equilibrium keeps being shifted to the left, that would mean that we would have a lower concentration or little hydronium ion would be in solution. And if we think about if we measure the pH of this, right, which is the concentration of the hydronium ions, it would indicate that it's a weak acid. It is a weak acid. So let's look at if the conjugate base is a weak base. So once the acid donates this proton to the water, it is unlikely that the base will reclaim that proton, right? And so we would see a shift to the right, so that proton would basically be happy with water in forming this hydronium ion. And so we'd see a large amount of hydronium ions in solution, thereby the pH would be higher, or we'd see a high concentration of hydronium ions. So we'd see basically a lower pH, which corresponds to a strong acid. So the strength of the conjugate base is really, it's really getting into, is this hydrogen oxygen interaction stronger or weaker than this hydrogen and A for base interaction? And you might be thinking this might have to do with how the electronegativity of the base A compares to the electronegativity of oxygen, right? In determining if that hydrogen oxygen bond is stronger or if that hydrogen base interaction is stronger. All right, so tying it all together, we can determine the extent or the strength of a acid, a weak acid, based on the strength of its conjugate base, right? We can determine the strength of the weak acid based on the strength of its conjugate base.